Hello, my name is Ranganathan Gopalakrishnan, and in this presentation, I intend to share details about ongoing dusty plasma research in my group, as well as talk about PhD student opportunities that are currently available. Before I do that, a few highlights from our group since the fall of 2016 when we started. So far, we have published 12 peer-reviewed publications in top journals. We have secured 1 US patent for a technology developed in our group. From our group, 3 PhD and 5 MS students have graduated and are currently employed successfully. Currently, there are 3 PhD students and 1 MS student in my group, and I am having a recruitment drive to identify 2 PhD candidates who could join us very soon. We have 5 active projects that are ongoing that are total worth of about $1.9 million. In addition to these, I have been awarded the highly competitive US Department of Energy Early Career Award from the Department of Energy in 2020, which is about $750,000 of funding to pursue fundamental research on dusty plasmas. As a research group, we focus on gas phase transport processes, and as engineers, our motivation comes from applications in material processing, wherein we use dense dusty plasmas and dense aerosols to produce metastable phases of materials in bulk quantities. And also we focus on powder technologies, wherein our goal is to use ultrasonic waves to disperse powders as aerosols at high concentration and with a steady output. Such technologies have wide applications in manufacturing and inhalation therapies that we pursue. Among the 5 ongoing projects in my group, there are a few that involve only modeling that I've shown in red here, and few that involve only experimentation that I've shown in blue here. And then there are 3 projects that involve both modeling and experimentation that I've shown in purple, about which on which I have an ongoing PhD student recruitment that I would like to bring to your attention through this link here, which you can follow. Now, what is a dusty plasma? A dusty plasma is a partially ionized gas that contains dust particles. And when I say partially ionized, it implies there are free ions, electrons, and neutral gas molecules that are moving in a medium. And there are dust particles which could be nanometer to micrometer size that are dispersed amongst them. Due to the electrons being much more mobile than the ions, the dust particles are typically negatively charged, and they acquire hundreds to thousands or even 10,000 units of negative charge per particle. The dust particles are thus electrically coupled and interact with the surrounding ions, electrons, and electric fields that may exist in the plasma. The applications of studies of dusty plasma include understanding astrophysical processes in near-Earth environments as well as in highly ionized environments. Technologically, plasma-aided semiconductor manufacturing is the process by which most of our semiconductor chips are made. So understanding dusty plasmas has a vital role in them. And there are also basic scientific curiosities that dusty plasma help us to understand. As far as their areas of application go, dusty plasmas, examples of those can be found in astrophysical environments such as Saturn's rings, where there are millimeter-sized objects that are highly charged because of ionizing radiation. There is plasma etching processes in which laser or highly reactive ion beams are used to remove material. Such removed material condenses above the wafer surface, forms particles, becomes charged, and organizes into a dusty plasma. And finally, dust grains interfere with the production of energy in fusion reaction devices, wherein they absorb energy that is produced and lead to the failure of the process if they are not managed. Now, I talked about how dusty plasma contains charged dust particles or charged particles, and by virtue of their electric charge, they have a potential energy that can be estimated nominally as the charge squared divided by the average spacing between the dust particles. So if there are a dust of concentration NP, which has units of per volume, a number per volume, NP to the minus 1/3 is approximately the distance between 2 particles in an average sense. So if we consider the average potential energy because they are charged, and also the average kinetic energy because these particles are also constantly moving around because there are forces acting on them, we can define a coupling parameter gamma, which will appear throughout this presentation. And gamma is defined as the ratio of particle potential energy to kinetic energy. Now, if we consider a situation in which the potential energy is very small compared to the kinetic energy, that would be like as though the system of particles behave like a gas. Or if we consider a situation in which the particles have a lot of potential energy compared to their kinetic energy, they would behave like a liquid or even like a solid. Now, the animation that I'm showing you here resembles as though there are a bunch of dots that are moving around. Each dot in this animation is a charged microparticle whose size might be around 6 to 10 microns, and they carry each about 10,000 units of negative charge. Now, because of the interaction electrostatic force between them, they self-organize and are also confined using electric fields that exist due to externally applied electric fields, and they together behave as though they are a liquid that is flowing. And if you just put your imagination, you can see that there is a flow this way, there is a flow in this direction, and there is a reversal of flow somewhere happening in between where the velocity switches sign from this direction to this direction. So the dusty plasma behaves like a liquid or a gas in this example. And depending on the value of gamma or the charge on each grain and the number concentration of the grains, as well as the kinetic energy of the grains, we can create systems that resemble like a gas or a liquid or a solid, and this has been very well known for some time now. So by varying this parameter gamma experimentally, we can get dust particles in a plasma to behave like a gas, where if you see here, you can see that the dust particles resemble as how a gas would move in reality, or how gas molecules would move in reality. They bounce off of each other, they move very fast, they are moving randomly. If you keep increasing gamma, you can see that in this example, they move like a liquid, they are moving around randomly, but they are also somewhat bound to each other, that they don't exactly fly away like a gas molecule. And further increasing gamma leads to a state of a solid or a crystal, where the particles are almost fixed in their positions. They undergo some motion. As you can see, there's some flickering going on here where the particles slightly move around, but there is more or less resemble a solid or a crystal with a very definitive structure. And this is produced experimentally by varying either the gas pressure in the plasma or the electron concentration or the electron temperature. And how these will allow us to control the state of organization of these dust particles is something I'll get to soon. But the idea is, by varying the gamma parameter or the electrostatic coupling, dusty plasmas can be used to create a system of particles that resemble a gas or a liquid or a solid that can be used to study how materials themselves behave in gas, liquid, and solid phases. Because unlike real atoms and molecules, these dust particles can be imaged using a camera, and that's how these videos were produced. Basically, we recorded the trajectories of the particles while they are moving in an experiment, and then use that further to do analysis. That's the whole topic of the research that I'm going to talk about. So if we think about the dusty plasma and there are charged particles, we would like to ask, what are the kind of interactions that go on in the dusty plasma? So there are dust particles which are charged, and then there are ions which are positive. And I talk about only positive ions because usually these plasmas are created in an inert gas, where a neutral gas is ionized into a positive ion and an electron pair. So when I say ions, I'm more or less referring to the ion that is positive formed from the inert gas and electron. So the charged particles which are negative interact with ions, they exchange charge, basically they attract charges, they exchange momentum, they exchange energy. So there is mass, momentum, and energy transfer between the plasma and the particles. There are charged particles moving around, so due to their charge, these particles interact with each other through electrostatic forces. And also because there are ions and electrons present in the vicinity of the charges, an important effect called screening takes place, wherein the effective charge of this particle is reduced for all charges that are outside a certain sphere. So this is basically an application of Gauss's law, where the total charge that is residing within this circle is the effective charge of this circle or the sphere. For any charge that is outside, this is a reduced, this sphere's charge is effectively screened. And then there are other interactions, like there is a background gas, which is argon or generally any gas. There are particle gas interactions, which causes it drag and Brownian motion. And then there are ion-ion interactions where they exchange forces. There are ion-gas interactions where the ion diffuses due to Brownian motion and experiences drag. And then there could be external forces such as gravity, applied magnetic fields or electric fields, and so on, or laser forces or any kind of external stimulation. So overall, if we see, there is a particle level where there is transport of charge, momentum, or kinetic energy to an individual particle. And then there is the particle phase level, which if you collectively view the particle as a single phase, they behave like a gas, solid, or a liquid because we are imaging them using a camera. And because of the fact that these are microparticles, they can be imaged using a camera. And if you look at the movie, that movie resembles a gas or a liquid or a solid. So it gives us a way to study the behavior of these phases. There are also free electrons present in a plasma, which are very hot or which are very much more energetic compared to the particles and ions. So as such, they don't really interact with the slow moving species such as ions and electrons and neutrals. So we have very simple approximations of how we treat the electrons in our analysis, but I won't talk about that much in this presentation. So we do both experimental work and modeling work or analysis work. And to get experimental data, we use several strategies. The first strategy is to use openly available data from experiments that were done on board the International Space Station called Plasma Crystal 3 and Plasma Crystal 4, where an international collaboration carried out experiments in microgravity and made the data available for people like me to use and analyze. And then we also obtain data from experimental collaborators who specialize in experimental research in dusty plasmas. We also go to federally funded user facilities in the US, where we can work directly with the scientists there to do experiments and collect data and then use it for analysis. And finally, we have our own lab at the University of Memphis, where we also carry out experiments and get data. So using this strategy, we obtain experimental data, which forms the basis for our research. It's data-driven in that sense. And using that data, we carry out analysis of particle processes, both at the particle level and the particle phase level, where I mean by particle level down to transport to an individual particle. And particle phase level, I mean the collective behavior of a group of particles or a population of particles. In today's presentation, I'm going to talk about two such processes, one at the particle level and another at the particle phase level, highlighted in yellow here. The first of which is called the modeling of ion drag. So at the particle level, we are talking about today the momentum transfer onto individual dust particles and how we use multi-scale trajectory simulations to predict that momentum transfer and use experimental data to compare our prediction and validate our approach. At the particle phase level, I already told you that these dust particles can behave like a solid, liquid, or gas. And here we are going to show you how we are deriving thermodynamic state variables for the dust particles if they are viewed collectively as a single phase. Like, for example, when we talk about the pressure, temperature, and density of a gas such as air, we use the ideal gas equation to model it. Likewise, can we derive state variables to describe the dusty plasma, which can be a gas, liquid, or solid, depending on the experimental conditions. So to start with, I'm going to talk about the ion drag modeling. And if you are familiar with the word drag force in the context of fluid mechanics, it is usually the resistance to the motion of an object or a shape through a fluid medium where the object is trying to move in a particular direction and the resistance comes in the opposite direction. So if the motion is in one way, the resistance or the drag force is usually the opposite to that motion. Now, ion drag force is similar in that aspect, where the ions which are drifting in an electric field, remember, if there are ions and an applied electric field, the ions will drift because the electric field applies a force on them, and they would try to move collectively or flow to the right in this example. While they are flowing to the right, charged particles that exist in the plasma will move the opposite way, and you can see that there is a relative motion between the ions and the dust particles. Because of this relative motion and the fact that the ions and dust grains have an electrostatic force between them, the ion not only is moving to the right due to the field, it is also moving towards the particle and exchanging forces with the particle. Not only is it exerting force from a distance, especially if an ion collides with the particle directly, it also exerts an impulse force that is like somebody who is bicycling against the wind experiences because the wind is blowing at their face. So there are two contributions of the ion drag force, one from long range forces between the particles and ions, and another by momentum transfer to the particle by direct collision with the ion, which is basically whatever momentum that the ion had during impact, it is transferred to the particle over the time scale of the collision, which is momentum divided by time, or in other words, the ion drag force. Now, unlike the drag force due to a neutral gas or in general drag, ion drag is very complex because it doesn't always decelerate the particle. Sometimes it can be against the direction of motion. So if the motion is this way, the ion drag force can be opposite. But in some cases, due to the nature of forces between the particles and ions and the concentration distribution of the ion around the particle, the ion drag force can actually act in the same direction of the motion, causing the particle to accelerate, which is counterintuitive. That is, if you think of a drag force that you experience when you bicycle against the wind, you would expect it always to slow you down, but ion drag force is, because of the electrostatic forces, can actually end up accelerating you. It is an important aspect and it is an important force in the context of dusty plasmas because it is one of the ways in which the energy actually cascades from the plasma down to the particle. If you think about it, a plasma is driven by an external circuit which has power either through a DC source or an RF source or some kind of a power supply. That power is transferred to a plasma where there are electrodes and electric field applied, which accelerate the ions, and the ions deposit that energy on the particle through impacts and forces. And that's how the particles in the plasma experience the power that is applied to the plasma itself. And the opportunity here is that to date, a theory of ion drag force that completely explains all of the experimentally observed complexities isn't available. And that motivates us to develop this and try to come up with a solution to this problem. To validate our modeling, we use experimental data from the Plasma Crystal 4 experiment that is an ongoing campaign on board the International Space Station, where a dusty plasma experiment has been set up. I won't go into the details of the experimental setup itself, but it was originally designed to probe particle level processes such as charging and ion drag, as well as particle phase level processes that are like collective interactions of particles under various conditions. So suffice to say, we get our experimental data from this campaign or from this experiment and use it to test our modeling. One such experimental data looks like this. That is, the particles in this example, they are dispersed in the plasma, which usually is formed in this volume. And once dispersed, they become charged and they flow in response to the electric field. So basically their direction of motion is this way. And I'm going to show you a video that gives you an idea of how the data for this from this experiment looks like. So here is a video of particles that are drifting in response to the electric field. And you can see that they are all drifting one way. And I'll repeat the video here. They are all drifting one way, and the video is actually quite long. It's many minutes, but I'm just showing you a few seconds, and we collect the position and velocity of these particles frame after frame, use them to compute velocities and use them to validate our modeling. I'll give you more details on that shortly. So the experimental data that we are using right now comes from a paper that was published in 2004 and 2005, where the images of the particle tracks were like this. And in terms of the experimental conditions, there are several parameters that the experimenters varied. For example, they varied the plasma power to get a number density or the concentration of ions and electrons that exist in the plasma volume. The gas temperature, or the ion temperature, the choice of the ion friction factor or the drag coefficient, the particle radius, and the particles most importantly get charged because of the plasma. And that grain charge is determined by the plasma itself. So it has to be something that we can't predict, we can't input in the front end, but it has to be something that comes out of our calculations self-consistently. And there is an electric field that is applied that causes the drift of these particles, and that was also measured from the during the experiment. So to do the model development, we take the experimental inputs that I've listed here. We calculate the ion drag force, and I'm going to talk about the calculation approach and compare our calculations against experimental data from this paper that was published in 2005, and more data that can be obtained from PK4 campaigns, of which there are about 15, and there are terabytes and terabytes of data that we are mining through to obtain useful sets for validation. And I'll just mention one of our previous projects in which we used such an approach of using PK4 data to validate our modeling of grain charging and comparing it against the experimental data available. And what we, to make a long story short, what we got was our predictions are within about 20 to 25% of the experimental data in most cases, which makes our model quite reliable to use and settled a long-standing question about particle charging in plasmas. So using a similar approach, I want to remind again that this ion drag force has two contributions. It has contributions due to both the force between the particle ion from a distance, which is the Coulombic force, and also momentum transfer to the particle by direct collision with the ion. Now, we can turn those words into equations where I write the ion drag force on a dust particle is the sum of the force between an ion and a particle at any given instant. Suppose there is a particle and it is moving at a certain speed, and there are ions all around it in our simulation, and we can compute what is the force between each ion and the particle. That is, what is the force on particle P due to J ions, where J can vary from 1 to Ni. And we sum that up because we know the positions of the ions from our simulation, the position of the particle from the simulation. And whenever there is a collision, we also add a discrete jump in the force, which is just the momentum divided by the collision time whenever there is a collision between a particle and ion in the simulation. Now, I'm not going into all the nitty-gritty details of how the simulation is constructed, but what we do is essentially we first populate the domain with a bunch of dust particles of known size, and we keep them fixed because the particles are so much more massive than the ions. It's not necessary to consider their motion when we are looking at the motion of ions. We let the ions drift in the presence of an electric field where, because of the particle, they are going to be attracted to it and charge the particle. We also include the electron currents to a particle using a Monte Carlo approach. So what happens is that the ions collide with the particle, the electrons flow to the particle like a continuous current, and they give the particle a steady state charge. That is, each particle picks up a steady state charge. And after a while, we switch to a particle scale where the ions are removed from the domain. We just let the particles move with a fixed charge where they respond to the electric field and they start drifting in one direction. Now, this is sort of like a predictor-corrector approach where we first let the grain charge be predicted by ion collision, and then let the grain's drift velocity get updated due to the electric field, and then iterate back to the ion scale where we correct the grain's charge because of the ion transport, and do this iteration until we get complete convergence in the grain's drift velocity, which is this. We get convergence on the grain charge, which is the transport of ions to a single grain, and the force on grain due to the ions, which is the ion drag force that we are interested in today. So our simulation not only captures the ion drag force, it also self-consistently predicts the grain charge, which has in the past been measured also. So we are able to validate against data that comes both from ion drag experiments as well as grain charging experiments. So we come back here where at steady state, if our modeling is right, our ion drag force prediction and the neutral drag due to the particle drift, because there is also a gas in this system, and then the electrostatic force because that there are charged particles, these three forces should add up exactly to 0, which would be a consistency check for our simulation. And doing our due diligence, we are able to balance the force values we get from the simulation is exactly matching the other two forces here, so that we are able to balance achieve this force balance as expected. So now that we did we have the simulation set up, we are on the process of we are into the process of validation, wherein first we took experimental data from this paper in 2005, and using this alongside this experimental data, which is shown here in black triangles, we are plotting the drift velocity of the particles. And I'm going to show you this video here to show you what I'm talking about. Think about the particles drifting from right to left. You can calculate an average drift velocity by taking the velocity of each particle, adding up all the velocities and dividing by the number of particles, which is exactly what we have here. And the red circles are the predictions from our simulation. And this is still preliminary. We are still working on this. And what we have so far is the trend is coming up very well if we take all the experimental conditions and feed it to our calculation approach. And as the runs converge fully, we expect this agreement to get better. So with refining the time step used in the simulation, with refining the convergence criteria used in the simulation, we expect the error to become even lesser and the particles to be closer as we go on. So our approach is, I'll just summarize in one line, is to run a multi-scale ion and particle simulation to get the particle drift velocity, the grain charge, the particle charge that is in steady state, as well as the ion drag force on the grains, exactly, so that all of these can be used to validate ultimately the experimental observable, which is what we observe using a camera when we record the trajectories, which is the drift velocity, which is the combined effect of charge and ion drag. So by validating against that, we are able to match exactly with or validate our approach. Now, shifting gears, I would like to talk about what goes on at the particle phase level, where I'm going to talk about our work on developing a thermodynamic framework for dusty plasmas. And I told you about in the initial slide on dusty plasmas that the grain potential energy to the grain kinetic energy or kinetic temperature ratio is defined as the coupling parameter. So depending on what this kinetic temperature is, you can even see that gamma is nothing but an inverse of temperature. So gamma inverse is basically a measure of temperature of these systems or these particles. So by varying gamma, we can realize systems that are weakly coupled or they behave like a gas. And if you are thinking about thermodynamics, in thermodynamics courses, we always teach the gas has internal energy that is purely kinetic energy. As the gas condenses, becomes a liquid, the component or the contribution of contribution of potential energy to internal energy goes. And if you go to the other end where the liquid has solidified into a solid, the internal energy is almost entirely potential energy and has very little free kinetic energy to each molecule or each atom. So that is exactly analogous to what we see in dusty plasmas, where for the value of gamma going from very low to very large, we are seeing the whole spectrum of gas, liquid, and solid-like behavior. So in that sense, dusty plasma is a classical analog of quantum matter. That is real matter due to the quantum nature of electrons and subatomic particles is something that is driven by quantum mechanics at the microscopic level. But dusty plasmas, due to the similarity with real matter with regards to the interactions and their collective behavior, is a classical analog where everything is purely classical. There are no quantum effects, but they exhibit the same dynamics that you would see in dense gases and liquids or solids, such processes such as diffusion. That is, you can observe diffusion of mass, momentum, and energy through these dusty plasmas or the particles. There is shear flow. There is thermal energy transport or heat conduction. There is phase transitions from liquid to solid to gas and whatnot. There is wave propagation. A disturbance propagates through a medium. There is turbulence. There is surface tension. All kinds of macroscopic observables that we see in everyday life can be visualized using dusty plasmas, because they are a system in which you can image each particle directly. So you can see the particles, know the position and velocity of all particles or constituents in that system, and use them to theorize how these processes work at a fundamental level. Now, if you recall quantum mechanics, the basic postulate is that Heisenberg's uncertainty principle says that you cannot know the position and momentum of a subatomic particle with absolute precision. That is true in the quantum world, but in dusty plasmas, which are purely classical, you can know the position and velocity of each particle at all times, giving you the ability to theorize about how processes work at a kinematic level. So each property or each quantity that you can think of has both a kinetic contribution and a potential contribution. Like, for example, internal energy has both kinetic energy and potential energy that together make up the total internal energy. And here is an experimental data set from a published paper where you can see that these particles together move like a liquid. They have been created by dispersing maybe 5 to 10 micron size particles in a plasma. And once the particles are dispersed, a laser was used to randomly heat them or thermalize them so that we can get each particle to move like as though they are in a liquid with no preferred direction. Another example here is that the particles are dispersed in a plasma, and based on the conditions, they organize like a solid. And you can see that there are defects here at several places that keep shifting around. So they behave exactly like a solid, which can be used to study how solid state physics works at a fundamental level. Now, we can go on talking many examples about how dust particles behave and how they behave like real matter. Now the question becomes, what about their thermodynamic description? That is, you can take equilibrium thermodynamics and use state variables such as temperature, pressure, internal energy, and entropy to describe materials like air, water, nitrogen, oxygen, iron, water, and different pure substances. Question is, are these state variables also true or also valid for a non-Hamiltonian system such as the dusty plasma? And what do I mean by non-Hamiltonian? Usually, if you take a group of water molecules, there are no dissipative processes in them by themselves. They are just molecules that together interact and conserve their total energy and momentum. Whereas if we take dusty plasmas, they are a set of dust particles dispersed in a plasma. We see, when we try to image them, we see only their trajectories. We don't see the gas molecules which are constantly stealing energy from them through drag force. So in that sense, it is a system in which energy conservation does not apply, because they are constantly losing energy to the neutral gas. And then there are also other confinement forces which are electrical in nature, heating forces which are random in nature, and so on. So for such a system, do the state variables really describe the state of the plasma? And if you go back to why that question is important, what are state variables? State variables are basically those that if you attain, regardless of how you got there, they describe the state completely. That is, if you have if you have nitrogen, at a certain pressure, temperature, and density, it doesn't matter whether you got there by heating or cooling, that state is uniquely defined by just two state variables and the equation of state. So can we derive a similar thermodynamic equation of state for the dust phase in an experiment? That is the question we are asking. And if we are able to, would it be universal? That is, can we take different sets of experimental data collected over the last several decades and map them onto a common thermodynamic surface, which would be universal? So will we be able to collapse all experimental data that we can access into a single equation of state or a thermodynamic surface, which will basically unify all prior observations under a single umbrella? To do that, our methodology consists of using trajectories that can come from experiments or from simulations. Those trajectory data basically consist of the positions and velocities of n particles that are in the frame. Using those, we compute structural measures that give you the insight into the structure of the phase, basically whether that phase is a gas, liquid, or a solid. If it's a solid, what is the crystal structure? If it's a liquid, what is the chance of or radial distribution function? And then autocorrelation functions, which basically tell us how position, momentum, and thermal energy decay in time within that medium or that phase. And also using that, we can compute thermodynamic state variables. We can compute transport properties like what is the shear viscosity, thermal conductivity, mass diffusivity, and so on. So that is our methodology: to take trajectory data, use them to compute quantities of interest. And the data itself comes from images that are collected in experiments, and we work with a very wide range of collaborators around the world, from Asia to Europe to America, where we collect data and try to analyze and bring everything under one unified description. So in that sense, we are not only experimenters, we are also modelers in our thinking. So we take the images, we extract the position, the velocity of the particles frame after frame, and using those, we compute the quantities from elementary formulas in statistical mechanics. So we take the raw images, do image analysis, extract position and velocities, calculate thermodynamic state variables. In this case, I'm going to talk about pressure, internal energy, and density, construct a phase diagram with these quantities as the axis, and then we come to the main hypothesis. The main hypothesis is, if we are talking about a phase diagram or a thermodynamic equation of state, then any two points that have the same value of the state variables should really represent the same state. So what we do is, we collect all the data we have, we calculate the distance between all the points that as it appears on the phase diagram, and then we take states that are separated by very small distances, that is the smallest we could find. And then we ask the question, are these two really the same state? And how do we answer that question? We do structural and temporal analysis to figure out whether the numbers say whether they are the same state or they behave identically. And using that, we try to settle the hypothesis that these three are the choice, or a good choice for a state variables to describe the dusty plasma. And then we add enough data points so that we are able to come to a conclusion that is unambiguous from a statistical point of view. So to construct these state variables or these phase diagrams, we have to first be clear how to compute them. One of the first and important variables to compute is the dust phase temperature. Now, I'm not talking about literally the gas temperature or the dust surface temperature. I'm talking about, if you look at this gas as a whole, if you consider each particle like a molecule, what is the total kinetic energy or the average kinetic energy per particle, and can we use it to define a kinetic temperature? Basically, if you view this like a movie, what is the temperature corresponding to the motion of these dust particles is what we are computing here. So it's very literal. We take the velocity of each particle in a frame, calculate the energy, total energy and the average energy, and then average it over several frames to get a converged single value for an experiment. And then we try to compute what is the dust phase pressure or confinement pressure. Now remember, each particle here is negatively charged. So if we don't do anything, they'll just fly away because they all repel each other. So to keep the particles confined, the experiment usually involves applying a confinement force or a confinement potential so that the particles are reflected back. So if each particle's potential is minus Vp, the confinement potential is usually a number that is more negative, so that the particles would rather move towards each other than towards the confinement electrode. So using a force balance for the particles that are in an arbitrarily chosen circle, we are able to calculate what is the confinement pressure, which is basically the radial force divided by the circumference, which is like force per unit length in 2 dimensions. Of course, in 3D, pressure is force per area. This is 2D that we are talking about because the dust particles are all formed in a single plane. And then we are talking about what is the dust phase internal energy, which is basically the sum of the kinetic energy and the potential energy between the grains summed over all the grains in a given frame and then averaged over several frames. So if you see here, this potential energy is the Coulombic potential multiplied by an exponent that accounts for the screening of grain charge due to the free charges that are present in the plasma. And lastly, we want to compute the dust number density, which is simply number per unit area, or NP to the minus half, which is like the average distance between each particle in this picture, divided by a length scale, which is chosen as the plasma Debye length, about which I won't talk about today. But suffice to say, it is a parameter that captures how many free charges are there in the plasma. So if we do this analysis and collect data that goes back to about 5 to 10 years, we are able to get a phase diagram that looks like this. And I've indicated numbers here to denote that they are all different from different experiments, different data sets. And we have plotted them on a 3D phase diagram. So if you take the distances, the Euclidean distances between these data points, that is, you can calculate the distance between all the pairs, and then we pick a pair which has the minimum separation to check our hypothesis, which is if this is separated only by 4 units, then are these two states similar or same? That's the question. And we answer that question by doing structural analysis and temporal analysis. Structural analysis meaning if I take a particle and calculate measures that resemble or that capture its environment, do 2 particles that are in these 2 frames are really in the same environment structurally. That's one. For example, this could be a FCC lattice, this could be a BCC lattice. In that case, they are really not the same phase. The other analysis we do is temporal analysis. That is, if we make a perturbation of this particle, say suppose we give it a small shake or move it around or jiggle it around a little bit, how fast will it be attenuated and how fast will it be brought back to its mean or equilibrium position? If that happens at the same time scale, then we can think the same kind of dissipative processes are at work in these 2 phases. And remember, these 2 were experiments that were done on different days with different set of experimental conditions. Okay, so it's not really the same picture, it's completely different, but they are only separated by 4 units on the phase space. So we do that analysis, we compare their structural pattern, that is, this is the pair correlation function, where we talk about what is the chance of finding a neighbor at certain periodicities. Okay, and for a solid, usually these peaks correspond to the lattice spacings, and for a liquid, usually we get a different pattern that we'll see very quickly. And the velocity autocorrelation, or the rate at which velocity decays over time, the rate of decay is compared by the slope of the autocorrelation curve, and in this case, they are somewhat significantly different. Another example where we take two data sets, one from 2016 and another from 2022, where they are separated by 12 units. we see that this image represents a liquid, but that liquid has some periodic features as well. The particles are moving randomly, but there are also some periodic peaks from the data. And the liquid on this side, the particles are moving randomly, and that there is a high chance of meeting them at a fixed distance. And then the chance of meeting them is more or less the same, which means the particles are all randomly mixed throughout the experiment. So clearly these two are not the same states, because this is almost like a pure liquid, whereas this is a liquid that has some crystals in it. For example, like it's water at 0 degrees Celsius with some molten, with some ice crystals mixed in there. And the autocorrelation for these two data sets are similar, that they have similar dissipative processes, but structurally they are different. And I just gave you an example of how we are conducting our analysis, and this is only 30 data sets. What we are doing currently is to go through different data sets available to us, and also do new experiments to collect more data, where we can conclusively prove that this thermodynamic equation of state can be constructed with density, internal energy, and pressure as state variables. And if we can do that, we can use machine learning algorithms to stitch together an equation of surface, or use trajectory simulations to carry out more modeling to come up with an equation of state that will summarize all the experimental observations together. So now, why is this whole exercise important? That is, why do we want to construct a thermodynamic surface for dusty plasma? Well, the first reason is each dusty plasma experiment is different. There were different conditions, confinement methods, external forces that were used. And if you think about it, real matter, like for example, water, behaves identically regardless of the container that holds the material. You wouldn't expect water to behave differently if it is held in a beaker versus a bucket. Now, it's the same true for dusty plasma, because the confinement is basically like produced by an electric field, and that induces the dust particles to interact with each other and exchange mass, momentum, and energy. So the question we are asking is dusty plasma matter universal, or can be considered something that is general if we reduce the trajectories which are contextual to thermodynamic state variables which are intensive or path independent? And then there is also a neutral gas in the dusty plasma which makes it underdamped. And what is the role of that? We are trying to understand. So the question is, are two different dusty plasmas experiments nominally leading to the same value of thermodynamic state variables, really describing the same state of the dusty plasma matter? That's the question we are trying to settle using the approach I showed. So for doing that, we get data sets from collaborators, from other experimental campaigns, and we also do our own experiments. And we are trying to find as many data sets as we can to validate this approach and develop a self-consistent continuum description of dusty plasma matter, which would make this extremely attractive for people who are studying condensed matter physics and self-organization phenomena, strongly coupled phenomena in plasma. So I would like to come back to my original point about the several ongoing projects in my group. And I showed you two of those, particle level and particle phase level processes in dusty plasmas. And the direct application of these two projects is in the high throughput material processing, wherein we try to grow particles under high concentration of dust grains in plasma so that we can produce materials at an industrial scale, like for example, kilograms per hour. And this is where I have two PhD student opportunities that if you are interested, please visit my webpage to know more and to apply. So that is my email address and my address for my faculty page, from which you can find this, find the flyer or the ad for this opportunities that I have described here. Thank you.